So, yes, student talks are back. We're in the middle of summer vacations, but today we have with us an excellent speaker, also a brilliant mathematician, and according to Google, also a comedian. So this is the continuation of Neel's talk on machine learning. If you're watching it on YouTube, we'll put the link in the description for the previous talk. This talk is being recorded as well. If you have questions, you can always type them in the chat. There should be a bar which indicates where the chat window is. And there will be strategic breaks that will address questions. On that note, I'll hand over to Neel.
Awesome. Probably just a general note. This is called part 2 of my talk, but it's going to be pretty different from the previous one. And it's not quite a direct continuation. The previous talk was more basics ideas of machine learning, and this is more, now you understand the basic ideas of machine learning, let's have a whirlwind tour of all of the random awesome things you can do when you have your head around the basics. So to begin, I'm just going to try to do like a very quick run through of all the ideas that I think are important to have in your head. I'm hoping this is going to just be a helpful review to everyone, so I'll try to keep it brief. So the central problem that we're trying to solve in machine learning is the problem of function or distribution approximation. We've got a bunch of data, and we know the data satisfies some underlying function or distribution, but the data also has a bunch of noise attached to it. And our job is to find the best function we can that approximates this. But our goal isn't to approximate the data we have. Our goal is to approximate the future data we will get. And so our job is to infer from the noisy data we currently have what the underlying function is. So tracking the structure of the function we care about and ignoring the random noise that you inherently get. And this is a really hard problem because the function and the noise look exactly the same from our point of view. So if you look at these graphs at the top, the left underfitting is where we don't respect the structure enough, and the right overfitting is where we respect the data too much. We fit the noise, and this is like a really hard problem, and the entire field is built up around figuring out how to solve this. And the main tool we have is we need to somehow understand how the function differs from the random noise on top. And the way we normally do this is a technique called regularization, which is basically just having a prior of what things are structure and what things are noise. So for example, here, our prior was simple things are more likely to fit the data than complex wiggly cards. And this idea of having a prior over structure versus noise is going to be a key thing to bear in mind throughout. The second important thing to understand is what's called the supervised learning paradigm. This is like what most of machine learning is about. Supervised learning is just, you have a bunch of data, which is inputs and outputs, and you want to learn from this bit of data a general function that can take an input and give an output. And this breaks down into these 4 steps. Collecting data, defining a cost function, so characterizing what good and bad data means, designing your network, so the neural network, the function that you're going to be trying to fit to your data, and then optimizing this general category of functions, all things satisfying this architecture, to fit your particular data. So I'm going to mostly be focusing on computer vision in this talk, and the most famous dataset is what's called ImageNet, which is a collection of about 14 million images from like all kinds of random categories with labels attached. So to give you an idea of the breadth, you have like goldfishes, vegetables, bridges, spacecraft, and it's just like pretty much every object the researchers could think of that might be interesting. And networks are trained on ImageNet to just classify images. taken an image and figure out what it should be out of a list of like thousands of classes. The cost function is this thing called cross entropy. I wouldn't worry too much about the exact details. The important point is that my network, this thing outputs a bunch of probabilities. So a probability that the image is in each of the possible classes. I then take a sum over every image according to whether it's right or wrong. The sum is differentiable, and if you want to take a mathematical perspective, this is a sensible cost function because it's the negative log likelihood if we're modeling our data at a discrete distribution. That point is completely unimportant for the purpose of this talk, but I think it's interesting, and if anyone who's taken 1B stats, you'll hopefully kind of get why that's important. If this is low, then that means the probabilities we output are likely to be a good description of the data. The network itself is, you'll often see diagrams like this. What this basically means is you've got a bunch of vectors. You start with an input vector, the image, you transform it into an intermediate vector, another intermediate vector, probably a bunch more, and into an output vector, which is a probability of being in each class. In practice, we often like to have data that isn't one-dimensional, like an image. Or if you've got a colored image, you'd actually have a three-dimensional vector, because you'd want to have a 2D image for red, green, and blue. And we're going to call these tensors. This doesn't really change any of the underlying logic, it's just important for representing the data in the way we want to. The in-between bits are a combination of a linear map, so just applying a matrix, and an activation function, which is a really simple nonlinear function that acts on each coordinate. We generally use one called ReLU, or rectified linear unit, which is just this thing. That is the max of 0 and the output. This seems really unmotivated when you first see it, and I'm going to touch a bit later in the talk on why this is actually an interesting and reasonable choice. And yeah, so to summarize the important bits in there, networks are built out of the composition of simple functions. Normally, you would think of this as just a mysterious black box, where you have an input vector and an output vector, and you don't care about the middle ones. So we're going to later see that you can actually get a lot of interesting things when you look at the middle ones. We're taking a composition of a bunch of simple functions, but the possible things that can be represented by those compositions is incredibly big, which is called being expressive. This means the network can just represent lots and lots of different kinds of data. It's parameterized, so each of these arrows actually represents a lot of numbers that are the parameters of the network. And the entire thing is a differentiable function of the inputs and of the parameters at every point. The two key intuitions taken from this are composition of simple functions and it's differentiable. The it's differentiable part is important because the final step, optimization, is just you differentiate it, you basically find the slope, but in a really big dimensional space, and you take a step in that direction. And this is called gradient descent. This is a ludicrously powerful technique because it's a way to take an arbitrary differentiable function that doesn't have really dumb curvature. Really dumb curvature meaning like if you had a function like this, it'd be really hard to do gradient descent on because you just get stuck in these points all the time. For a bunch of reasons that I talk about in my first talk, this kind of thing doesn't really happen in the ML context we care about, and we have techniques for overcoming this if it does happen. And so the lesson to take from this step is, given anything differentiable that isn't really dumb, you can optimize it. End review of machine learning. A few framing notes for this talk. So this is a talk about machine learning, not a maths talk. This is an important distinction because as a field, machine learning is very empirical. We've got a lot of stuff, we know that it works, and we know it gets really impressive results. We don't quite know how this works. I'm going to be talking later about some of the best ideas I've come across for why this works, but this is an important distinction to have in mind because it's really easy, especially if you're a mathematician, to get too clever about trying to explain empirical data. You can come up with like a really clever and creative model and a lot of beautiful maths falling out of it, but it turns out that one of the underlying assumptions at the very start was wrong. This doesn't mean that conceptual and theoretical tools aren't useful, but it means that you need to be really careful, always remaining grounded, and always testing your beliefs and making sure they're true, rather than that you're deluding yourself. And I'm going to try to flag all of the like epistemic statuses, all of the points that I make, and indicate things I am and am not confused about. The second point is the concepts in ML aren't really that deep. There are lots of clever ideas, but it's not at all like maths, where you have this incredibly deep theory that was built over the last 300 years, and you can't even get to the interesting stuff until you're like 4 years into a degree. ML is all about taking really simple ideas and thinking really hard about how you implement them, and getting a bag of like tricks and tacit knowledge. I'm mostly going to be skipping over this in this talk because I cannot figure out how to give an interesting talk about implementation details, but this really does matter. And if you practice doing ML on your own, it's important to practice actually making stuff rather than just thinking about it, because thoughts don't always translate into reality well. And finally, as a note for the structure of this talk, unlike some previous talks that I've given, this is going to be more of a whirlwind tour of a bunch of interesting, semi-unrelated concepts. I'm going to try to keep focused on like the intuitions, concepts, and cool examples, rather than the details. And I'm just giving this note in advance because if you do get lost at one point, you'll probably be able to just start again pretty soon because the sections don't really build on each other. They're just a lot of interesting ideas. This also means there's going to be pretty frequent breaks for questions. So if you have questions at any time, please put them in the chat and my glamorous assistants will be sure to let me know of any interesting questions. And there'll be 2 breaks for like just taking time to give questions. And yeah, just a general note that I'm pretty sure you're all aware of. Machine learning is like a really, really big deal. Like there are a ton of things that we are capable of doing now that we weren't capable of doing 10 years ago. Like computer vision is dramatically better, language is dramatically better, we're discovering new drugs, we figured out how to play seemingly impossible games like poker and Go, and this doesn't mean that the concepts are interesting, but I personally find it a lot more motivating to know that subjects I'm learning about really matter and really shape the world that I live in, and yeah, I just thought this is a point worth making. So, with all that out of the way, I'm going to get into the actual talk. So, the theme of the first half of this talk is the power of simple ideas. So, the ideas I've outlined so far are basically the key ideas of machine learning. But it turns out there's a lot of depth and a lot of kind of complexity and interesting detail, like interesting consequences that come out when you dig into these ideas. And this is going to be an overview of just like a few of the areas of ML I think are most interesting, and looking at how they take these simple ideas and run them. So the first thing, so gradient descent is a really powerful algorithm. It's just a general purpose optimizer to take any differentiable function and make it like find a local optima of that function. And like this is insanely powerful because differentiability is a very, very weak condition. But it's also a bit limited. So one of the main ways it's limited is if you have like 14 million images in your dataset, and your cost function is the sum over those million data points, then the gradient is the sum of like a million gradients. And this is horrific to calculate every time you want to change what your network is. So the glorious hack we have to get around this is what's called stochastic gradient descent, where rather than summing over all million things, we just pick a random sample of like 20 and sum over that. And this is called stochastic gradient descent, and it's like you've sped up your algorithm by a factor of 50,000. Without this, modern machine learning would just not be possible. And I think it's easy when you first encounter this kind of thing to think that, oh, this just seems like a really dumb hack. But it's actually pretty principled. So the cost function I have here is a sum over like a bunch of data points, saying, say, did my network classify these images correctly? And but I don't really care if it classified my images correctly. I care, would it classify the average image correctly? So this is really a probabilistic thing where I'm sampling from a distribution. And to find the so it's really about minimizing an expected value. So I care about minimizing the expected value, the gradient of the expected value, which is the same as the expected value of the gradient because derivatives are linear. And you can estimate this quantity by taking the sum over all your data points. But you can also estimate it by taking the sum over just a small number of data points. And that's what stochastic gradient descent is. And if you look at this picture, this is just showing, so blue line, you sum over every data point. The purple line, you just take a single data point. You take the gradient of that, and you sum it in that direction. And the green line is you take the sum over, say, 5 or 10 data points. What's called a mini batch. And if you look at it, these all kind of work because they're all headed in about the same direction. And this is one of the powerful ideas that makes machine learning work at all. But it gets more interesting because, so if you recall, the central challenge of machine learning is finding the structure and ignoring the noise. And it turns out that stochastic gradient descent helps us do this because the logic I just gave of is an estimate for the average gradient only holds for the true function we care about. It doesn't hold for the noise. Noise, in part, is characterized by being independent for every data point. So if you just take 20 out of the million images, that's a really different, the gradients for the noise are going to be completely different from the gradients for the noise for the other data points. But the gradients for the underlying structure of images are going to be about the same. And so these gradients point in independent directions, they kind of pencil out, while the gradients we really care about point in correlated directions, and they build up. And so just having stochastic gradient descent is a massive computational boost, but it also makes you better at the thing you care about in the first place, of fitting to the structure and not to the noise. And I just think this is incredibly cool. The second hack we have is an idea called momentum. So one problem with gradient descent is it's really slow. Like you might have something like this. You want to get into the valley, but you kind of get stuck over here. Like even if this never quite gets flat, like it looks like this, it's a really slow, very shallow gradient. You're not going to go anywhere, even though you know that you were like speeding into it. And so it'd be quite nice if we could have our optimizer remember, oh, I was speeding when I was over here. I'm now suddenly slowed down, but maybe I should continue speeding for a bit and see what happens. This is a good way to tell the difference between like slow flat bits like this and like deep valleys like this. Because if you speed out of this, you're going to get over here and be like, huh, I still want to go backwards. I should probably stop. And you can implement this really easily by just taking a moving average of the gradient. And this idea is called momentum. It's a trivial shift to the equations. You go from subtracting the gradient to keeping track of a moving average of the gradient. This thing is called an exponentially weighted moving average. You multiply the previous value by like maybe 0.9, and you're basically taking a geometrically weighted sum of all previous gradients. And this is a computationally efficient way to take an average. And then you just subtract that average gradient. And this works incredibly well. If you look at the optimal rate for gradient descent, the step size, the amount you move every gradient step, and you look at the optimum size for momentum, for some functions you can get up to a quadratic time speed up. when momentum is working best versus when gradient descent is working best. And quadratic descent speedups are amazing. Like, that's the difference between practical and impractical for most problems. And it was just a shift of one line of code to tracking memory. So yeah, that's the end of subchapter 1. Now I'm going to go on to a different tack. So one of the really important applications of neural networks is computer vision. The ability for computers to see with prior techniques was just like awful. But neural networks have been revolutionary in the field of just like recognizing images and doing things with images. And I want to dig into how this actually works. So
Neel, sorry, before you start this chapter, I think Pav had a question about the previous one.
Go for
it. So it says, like, how do you decide the threshold of what local minimum is good enough? I don't know, maybe Pav, do you want to expand a little bit on that? Or?
Sorry, I meant like the graph that you described was essentially just you not wanting to settle for a shallow enough minimum and going for something deeper. So how do you differentiate between?
So you can differentiate, well, so the parameter you have of how much you remember previous gradients is the thing that determines how shallow a minimum you end up in. And you can just tweak this and see which one works better for the problem. That isn't a very principled solution. And there's theory about how to come up with better ones. But this is a problem that we don't have a particularly good solution to yet, because we don't.
I mean, phrased differently, when do you decide that you want to stop searching for better minima?
That's a complicated question that depends on the problem. Roughly, if your thing is good enough, then you'd probably stop. There's a lot of theory around, if you want to find resources on this, search for early stopping. It's an idea from optimization where sometimes you should just stop optimizing because then you'll avoid overfitting. I don't really understand it, so I'm going to stop answering that. But Google early stopping if you want to learn more. So, okay, back to convolutional neural networks. So, a problem with the standard machine learning paradigm is that, we're using what are called fully connected layers, which are these like linear maps where you basically have you can think of it just like an input vector, an output vector, and every coordinate on the input vector can be connected to every coordinate on the output vector. And this is really dumb for images, because if I have like a picture of the digit 6, and I've got a feature that's looking here, 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 and here, I'm like, that's obviously not a sensible feature. While if a feature that's looking at like this square, then I might say, oh, that is a sensible feature. Like that's probably getting something. This feeling of this is dumb is what I was getting at the start with having a prior over structure versus noise. Images have local structure, so you should do things locally. And this is an example of regularization. And so the trick is that we shift our perspective. Rather than looking at fully connected layers, we look at these things called image kernels. So an image kernel is all about, you take a simple, say, 3x3 matrix, and then you convolve the image with that matrix. What that means is for every point on the original image, you take the 3x3 square around it, and you multiply that square with this like small kernel. And you use the same kernel for every point on the image. And this is a way to convert the point to a number capturing what is the local surroundings like. So for this picture I have, we picked a matrix that takes the sum of things on the right minus the sum of things on the left. So this is a way of saying, am I at a vertical edge? And if you look over here, it does a very good job of highlighting like vertical edges, like the edge of the guy's face, the edge of things over here. And So you want your network to be made of features like these image kernels. And you actually want to take like a stack of image kernels. You want to have like one that can do one that can do vertical edges, one that can do horizontal edges, one that can do sharpened bits, things like that. So you tell the computer, just come up with like 30 image kernels and apply that to the image. And that's called a convolutional layer. And this is like the main building block of computer vision networks. Except we don't tell it, use this matrix to look for vertical edges, because we're building a function approximator. It knows how to figure out which kernels are the best. So we just tell it, this is what a kernel is. You've got 9 parameters for each kernel. Just figure out what the parameters should be to fit this well. And the next step is, so over here, we just found a way to convert an image to something the same size as itself, but with like a bit more useful detail. And we can keep doing this, and this doesn't really feel like the kind of thing that's going to get us to a principled answer. Because what we really want to do at the end of the day is be like, there are eyes over here, there's a nose over here, there's a mouth. Oh, these all combine into a face. So we need a way to combine these local bits together. And we do this with what's called a pooling layer. So this just takes, say, a 16 by 16 grid, and then just splits it into 2 by 2 squares, and just squishes a square into one. The exact way you do it doesn't really matter. Often you take the average, or you take the max within a square. The point is just, you do a bunch of local processing, and you combine it into like a slightly more global thing. And then you can combine these into a network. You stack, say, 5 kernels together, convolve with the image, you then pool them, you then convolve some kernels again with this pooled layer, maybe 10 this time, you then pool again, and you just like keep doing this until you have just a 1D vector, and then you can just apply a normal neural network to them. And this is just encoding the structure of images have local stuff. This should be built up into a coherent whole. This is the reason at the start I mentioned that we look at tensors, not images. For this to make any sense, you really need to be thinking about it as like a 3D stack of 2D images, or 2D tensors, so a 3D tensor. Technically, you could do this with all the vectors, but it'd be really dumb to do it with vectors. And yeah, that simple insight is just how computer vision works. In 2012, the field of deep learning began when somebody just made a more complicated version of this rough network and entered the annual Do Well on ImageNet competition and beat everyone else out of the water. And this is the idea. Cool. End subchapter 2.
Can I ask about pooling? So why do you not lose loads of information when you, for example, take the maximum of a thing? It seems like you can just completely forget basically everything you knew about that.
Sure. So it's actually, so the way image recognition normally works is there are a bunch of features that don't matter, like this guy's forehead or the background. And there are some features that really do matter. And the way the network normally works is it realizes, oh, I'm losing lots of information, so I should make the things that do matter big numbers, and the things that don't matter small numbers. And so the pooling layer would be like, oh, for this area of the screen, oh, my eye neuron is big, because one of them lit up. These are all like very rough heuristics. The general point is just, this is a way to design a function. Neural networks are excellent optimizers. It will learn how to optimize within the constraints of this.
Yeah.
Not like you're surprising it by throwing away information. So
right. Okay, thanks.
Okay, so subchapter 3, transfer lag. So the really cool thing about neural networks is that they generalize. You can give them like a bunch of data and then give them novel data. And rather than overfitting the original data, they've understood the structure of the data and it can solve new tasks. And this turns out to be a much more powerful form of generalization than you'd naively expect. And because it doesn't just generalize to the same task with new data, it can also generalize to similar but new tasks. And this is called transfer learning. So, and this is a really, really powerful technique for doing things in the real world with machine learning. So this diagram is just showing, you might train something on this like 4 million image data set of ImageNet, and then want to train like a doodle recognizer. And then what you do in practice is you could just cut off the final layer of the network. So networks are these like composition of simple functions, and they end in like an output layer, which is just like a bunch of probabilities. And we don't care about this because we change what the final task is. But if we just cut off this layer and introduce like a new a new really small network ending in a doodle recognizing layer, and then fix the original network and then train on this like tiny network on top, we can solve our new task really, really easily. Like you can literally go from ImageNet takes days to train to training something new in minutes. Those exact numbers might be suspect. I haven't researched that part, but there are dramatic speedups because you're going from like a 1 million image data set to like 1,000 image data set. And this is especially awesome because with modern machine learning libraries, you can just download like a state-of-the-art ImageNet model and then retrain it for a task that you care about. And this means that with my shitty laptop, I can train image recognition software quite easily. And I'm going to get into, a bit later, I'm going to get into why you might think this works, but the important point is this does work. If you just look at the penultimate layer, things have learned to generalize. And this cutoff final layer was just a particular example of transfer learning. There are lots of other techniques you can use, but the important part is a network trained on one task can learn how to be good at a similar task really easily. So another practical implication of this is data efficiency. So machine learning is all about learning from data, and data is expensive. If you want to train, say, a Trump tweet analyzer to see when Trump is angry, and when Trump is angry, sell stocks because this is bad for the US economy, then you need somebody to go through Trump's tweets and label them angry or not in order to like write a program that can learn this. And that's really expensive because you need to convince somebody to read a bunch of Trump tweets. But another task that's really easy to get data for is taking a bunch of text, like a Wikipedia article, and training something to predict the next word given the article up to that point. It's like completely trivial to convert text to this like supervised learning task. And there are some really famous, OpenAI has 2 really famous models, GPT-2 and GPT-3, which are just incredibly big language models trained to do this. And the fascinating thing is that these models have learned how to do general languagey tasks. So in the most recent paper, they came out with GPT-3, this network that has like 175 billion parameters, which was like an enormous engineering undertaking and took millions of dollars to train. And at the end of the day, it learned how to do addition. You can just give it like, give it some examples like 11 plus 13 equals 34, and just like a bunch of stuff like this to prime it to be like addition of the task that I'm doing. That's what's meant by the word few shot up here. And then just give it some unfamiliar things to autocomplete. And it has almost 100% accuracy on 2-digit addition. It has really good accuracy on 3-digit addition. It's got surprisingly good accuracy on much longer digit addition. And this wasn't a thing that it was explicitly trained for. Note in this graph, this is the only bit you actually care about for how good GPT-3 specifically is. And it wasn't trained to do addition. It's just trained to understand language. And in the process of understanding language, it had to figure out how to do addition, because addition turns out to come up a lot if you have enough text. A few other examples. You can train it to generate memes. And a famous internet meme is just a very machoistic guy going on a rant about how weak and pathetic somebody else is. And here is a version that was trained, but primed to replicate that, but from a maths perspective. And this just makes me incredibly happy that something is able to generate this. Another one. This is a game of chess. White is a random blogger that I follow. Black is GPT-2. The blogger just gave GPT-2 a bunch of chess games in chess notation, started feeding in its his moves in chess notation, and asking GPT-2 to like respond to them. And GPT-2 isn't very good at chess, but this is ludicrously better than a language model has any right to be. So enough pontificating about how ludicrously awesome transfer learning is. Why does this work? So the main reason that I think this works, this is getting into a bit more speculative territory, because this is theoretical, not empirical. It seems to me that to solve a hard task, the network has understood the structure of the data. It didn't just figure out how to classify images, throwing away all the information apart from the thing absolutely necessary to classify the class. It understood the general structure of how image data or language data works, and extracted the important features. And the general lesson here is that to solve a really hard task, sometimes the most efficient solution is just to be general rather than specific. In some sense, this is the entire spirit of machine learning. We have this big, like massive hammer of neural networks, and it turns out it can solve just a lot of different tasks with enough creativity and effort. I'm going to get into this a lot more in the second half of the talk. Another way of thinking about this. So the way a computer represents an image is you break it down into pixels, and you just give it a number according to like how red, green, and blue it is at each pixel. And from an information theoretic point of view, this is an incredibly dumb way to represent an image. Because if you think about, say, English, we don't just give every word the same length. We give common words like the and short lengths, and we give uncommon words nobody cares about much longer lengths. Because you want to represent the common things with less information. This is important because if you want to represent something efficiently and in a way you can understand and do something with, you want to find a way of representing it where the things that are common and come up a lot appear early on, like have short descriptions. And if I look at a random image, like this TV static I've generated on the right, like that's just a typical image when drawn from when I just give random noise to a computer's parameterization of an image. And when I look on the left, this is a picture from ImageNet. It's very, very obviously not randomly selected. And this suggests that the way we give it an image to the network is a terrible parameterization, because the images we care about aren't uniformly distributed over that. So we're not representing information efficiently. And so one conjecture is that the network learns how to represent it efficiently because we only give it images like this and not stupid images like this. Another theory of what's going on is what's called manifold theory. So manifold theory says, maybe images actually a much lower dimensional space than you'd think from how they're represented as pixels, because it feels like I should be able to represent an image like this with many fewer parameters, because I don't care about the vast majority of things in image space. This is a pretty speculative hypothesis, and there's some evidence for and against it, but I find it a pretty useful conceptual tool for reasoning about why this might work. End subchapter 3 on transfer learning. The final subchapter of this half, because I should probably cut the 5th subchapter, is on generative adversarial networks. Wait, do we have any questions on that chapter first? I'll take that as a no.
Yeah, don't think there's anything in this part.
Transfer learning is magic. So, yeah, new topic. So, an interesting kind of problem you might come across with neural networks is de-blurring images. This is something you might come across if you're dealing with like JPEG artifacts or just low-resolution camera footage, or you just want to do a CSI enactment and be able to truly enhance images. And the main way to control what a network outputs is by choosing the cost function. But it's really hard to train a network to take in a blurred image and output an unblurred image using standard cost functions, like what's the difference between squared distance between the output and the original image? Because the blurry things are really close to the original image. Like, the pixel values might be like 3, 4, 4, 3, and get blurred to a square of 3.5. Like, these are really close together. So the standard cost functions don't really work very well. And you can like try to hack together a better cost function that can like somehow address this and make it care about things like textures and delicate details. But another way of thinking about this is, we want a function. We don't know how to characterize the function. And we're in a field of maths that's all about understanding how to approximate weird, messy functions. So let's just approximate our cost function with another neural network. This is the core idea of GANs. And so what we do is we just train a network to distinguish between blurry and unblurred images. And networks are differentiable functions, and a cost function is just anything differentiable, because anything differentiable can be optimized. And this is just like such a beautifully dumb idea, and it's quite hard to train because you get like weird interactive game theory between the two networks. But if you can train them well, this is an incredibly powerful technique for doing weird things that are hard to characterize a good cost function for. Yeah. Core idea, make your cost function another neural network when things get hard. So the original use case GANs were applied to is where the generative part comes from. So the problem we want to solve is we want to generate, say, handwritten digits. We think we can parameterize handwritten digits with many fewer parameters than the actual image itself, because maybe we believe in manifold theory or something. So we want to train something that can take in a small dimensional vector over here, like say 100-dimensional vector, and then do some expansion and magic and output a fake image. And we want to make this as close as possible to the distribution of like normal handwritten digits we'd care about. So we're going to train a second network, a discriminator, to tell between fake images and real images. And we're going to train both of these at the same time. And if we can get the dynamics right, we're going to end up with something that can take in like a 100-dimensional random noise vector and generate a realistic looking image. And this works. The picture on the right is a complete nonsense picture of the face that will generated by a GAN. And if you go to this website, it will just generate you pictures of fake people's faces. And it is incredibly impressive. And GANs are really useful. So a fun use you can get from them is this idea of style transfer. You take a picture, you give it a style, like an artwork, and you tell it, make this picture in the style of this artwork. So now you've got a generator that's trying to convert this to a stylized image, and a discriminator that's trying to tell, does this image have the right style? And I'm not really sure of the details of how this is trained, but clearly this works. This all has a bunch of practical uses. You can train a GAN to generate good voices by getting the discriminator to tell, is this a creepy robo voice, or is this a sensible human voice? The idea of deepfakes, taking videos where you superimpose other people's voices and faces, is from GANs. There's a Gmail feature where it will give you kind of smart replies, or like auto-complete your words for you. I'm pretty sure these are also made with GANs. A final cool thing you get from this is, so GANs are a function from, say, r to the 100 to the space of faces. And the idea is that every point in this space should look like a realistic face, because we train our network by inputting random noise. And if, like, the average point didn't look like a realistic face, then the generator would fail, and the discriminator would be able to tell, oh, you're fake. And this is fascinating, because it means you can take two different faces and just linearly interpolate between them. And you're smoothly varying your input to the GAN. The GAN is like a nice differentiable smooth function, smooth-ish, and so it's going to just smoothly vary from face 1 to face 2. And this is insane. Like, you can get stuff like this. I don't really have anything conceptual to say about this. I just think this is incredibly cool and weirds me the fuck out. I'm going to skip through the 5th subchapter in the interest of time. But I'll try to get to it if we have more time than I expect at the end. So, in conclusion, ML as a field is like incredibly young, and it's a pretty shallow field in the sense of there aren't that many deep concepts. Instead, there are a bunch of simple ideas that you can leverage into incredibly impressive results. And I think this is fascinating because, like, these simple ideas work. We don't quite know how they work, but there's a lot of room to understand how they work. This is an active research area for things that really matter, and I find that fascinating. That is the end of the first half. Does anyone have any questions?
So for GANs, right? How does a discriminator work? Because it seems like you're just kind of shifting, is being able to tell reals from fakes for the first neural network. You're shifting that over to the second network. Why does that just kind of magically solve everything?
Because so the problem isn't tell whether something is fake or not. The problem is make something that doesn't look fake. It's easy to tell whether something's fake or not. Well, not easy, but like there is structure there that can be understood. Like, humans can tell the difference between blurry images full of JPEG artifacts and like normal images. Thus, this is a visual problem that current vision techniques are able to solve.
Yeah.
And this means that you now have you're now training something to make a realistic image. And given a clear objective, the problem isn't that hard. The hard part of GANs is training both of these at once, and there are a bunch of clever hacks to get around that I don't really have time to go into yet.
Mm-hmm. Why can you not just train the discriminator first and see? after?
Yeah, that works, kind of. Like, I think that's one of the main ways you can actually get GANs that work in practice. The problem is it's hard to get a good training set of good-looking fake images, but you can get quite a lot of progress by, like, pre-training both on, say, crappy fake versions of the other one, and then connecting two medium quality versions to themselves, to each other, and trying to get that to work. It depends a lot on like the exact problem you're working on, but yeah, that does work.
Mm-hmm. Yeah, thanks.
Cool.
Sean has a question as well.
Cool.
It's so it says, "Hi Neil, how do you make sure that the GAN doesn't map all points in the input space into a bunch of really similar faces?" So
that's an excellent question. So why doesn't the GAN just like always output the same face? So I don't know why I'm drawing. There's no point drawing. So a useful exercise is to replace the discriminator with yourself. If the network was just outputting the same face every time, while the realistic images weren't, then you would just like say every time you see that face, oh, that's fake. And if that face is like 10% of the real faces, then you're missing out on like 10% of the real thing. You're capturing all of the fake ones, and that's really good performance. So in order to do well on this objective, the generator needs to get like good comprehensive coverage, because otherwise the discriminator could just like apply dumb rules and beat it. Like if it fails in an obvious way, the discriminator will find that. Anyway, I suggest people take a 30-second break, because this is a moderately long talk. Get up, stretch a bit. And yeah, I will start chapter 2 in a very short amount of time. Onwards to chapter 2. So this chapter is on a field of ML called interpretability. So so far, we've mostly thought of neural networks as just like mysterious black boxes. We have inputs, we've got a bunch of intermediate things we never look at, and we want an output. And we just like think of the middle things as mysterious black boxes. The field of interpretability is about trying to actually look at the things in the middle and see if we can learn anything about what's actually going on. And a priori, you wouldn't really expect this to work, but it actually does work impressively well. And the field has advanced a lot in the last several years. And this chapter is going to be my attempt to present the research I've been most impressed by and to talk about evidence for it actually being useful or not. So the ultimate goal is to understand the network and to build tools that somebody could use to look inside it, and to make it more than just a black box. A lot of the really impressive work in this area has been done by just one team, a team at OpenAI called the Clarity team, run by a researcher called Chris Olah. I'm going to be quoting from a lot of their papers. I recommend looking at distill.pub if you want to see a lot of their work. They're some of the best written papers I think I've ever read. And yeah, general health warning. This is all pretty speculative research, because this is trying to impose theory on empirical objects. And neural networks are these like incredibly complicated, many-dimensional objects. And trying to make them something human comprehensible is like pretty hard. So you always need to be checking your beliefs, being empirical and being grounded. And secondly, this is a pretty small field. Most people in ML focus on performance rather than understanding what's going on. So there hasn't been a lot of work done on this. But I'm pretty impressed by the work that's been done so far. And I think this is an area I'd be super excited to see more work done in. And finally, I'm going to focus mostly on computer vision, because that's one of the easiest things to understand and where a lot of the work has been being done. And a pretty active area of research is figuring out whether you can translate these ideas beyond computer vision. The central problem of interpretability research is cherry picking. Maybe 99% of the time, a neural network is an incomprehensible black box, but occasionally, by chance, there's something pretty and understandable. So a pretty common problem is researchers might like just pick out the one shining example and ignore all the ones that failed. This is the ML version of p-hacking. And at the end of the talk, I'm going to link you to a load of papers and examples and code that you can go through yourself and see whether it feels like it's been cherry-picked to you, or whether you think there's something there. So for the purpose of the talk, I'm pretty inherently limited by time, so I'm going to have to resort to a bit of cherry-picking. But this is a thing that you're very welcome to explore yourself. And yeah, for context, we're mostly going to be focusing on a particular convolutional neural network called GoogleNet, which was state-of-the-art like 6 years ago, which, given that ML as a field started in 2012, is the equivalent to looking at maths papers from about the 1800s. And yeah, it was trained to predict a bunch of images like this from ImageNet, because ImageNet is the hot, cool image database. So the first thing that I'm going to explore is feature visualization. So we want to understand what a neuron, so like a particular point in a particular coordinate in a hidden layer represents. And our first tool for doing this is going to be to say, okay, so I've got my input, I've got a hidden layer, I want to pick a particular neuron in the hidden layer, think of that neuron as a function from the input, or maybe like a small subset of the input because it's a convolutional network, and I want to find the image that maximally stimulates that neuron, like super stimuli. And if this works, this is awesome, because then a human can just look at that image and say, oh, that's what that neuron is looking at. And the way we do this is we take in a bunch of random noise, just an arbitrary image, just a random image, and then we optimize that image to maximally stimulate that specific neuron. And again, everything is differentiable. That neuron is a differentiable function of the input, and so this works. And here is an example of the results. Like, this neuron turns out to be looking for things that look like this. And the art of interpreting what these mean is a bit difficult, but in rough, this seems to be looking at like intersections between things, because an image that has lots and lots of like nodes with edges coming out stimulates it really high. A general note, if you just naively do this, it's easy to end up with like lots of high frequency artifacts and like weird things that aren't human comprehensible. So the researchers have added some regularization techniques to make it more human comprehensible. This is definitely a thing that should make you more skeptical of these results, though hopefully over the course of the talk I can convince you there's some substance to them, and I'll link to all the papers at the end to read about the details of the regularization they did. So yeah, just a reminder, the way convolutional neural networks work, each layer has a bunch of spatial meaning. You can basically think of it as the original image, and each pixel now has a vector of like the output of a bunch of different image kernels. And when you pool and apply more image kernels, etc., then maybe each like 4x4 square of the original image has a vector attached to it. And so it has a lot of spatial meaning. Yeah, pooling just lowers the resolution. So you go from 1 pixel to like 4 pixels or 16 or whatever. Another challenge is figuring out what you actually should visualize. So one thing you could do is visualize a neuron, which is one coordinate of the vector for one particular point in the image. This is going to get you something that's like centered on the center of the image, because it's like looking at a particular spot, and optimizing for that. Another thing you can do is a channel. So a channel is that coordinate across all of the different pixels in the input. So what this means is that, so we're applying the same kernel to every point in the original image. So a channel is like the same function, but kind of applied to every input independently. And so visualizing that gets you a kind of tiled structure. And finally, a thing you can do that I'm not really going to focus on in this talk is visualize an entire layer. So say, when you're like halfway through the network, what things is that layer most excited to see? And you get weird, trippy images like this. I don't think this is very useful, so I'm not going to talk about it in this talk, but Google Deep Dream if you want to see more about this. This is one of the really early results in this field. So the first thing you should always check when doing something like this is, does the data seem to support my hypothesis? Is the data that I'm looking at, does the data that maximally stimulates the neuron I'm studying look similar to the visualization? And if you dig into the examples, this seems pretty true. Here is one moderately cherry-picked example where it seems pretty semantically meaningful. Like it's looking for kind of squarish things with edges and frames. And if you look at the data, that gets borne out. It's clearly like activating it like this thing, and this thing, and this thing, and this thing. Like, this doesn't seem like it should be a coincidence. And a fascinating thing happens when you look at the different layers of the network. So here, the network is like, you start with the input, you then go down through a bunch of layers, you're like crawling along the way, and then you get to an output at the bottom. And these different pictures are visualizing different layers along the way, different channels along the way. And the thing that I find fascinating is there seems to be some like very clear semantic meaning to them. Like the really early things are looking at really basic local structures like edges. The next layer is looking at things that are more like textures, and you can imagine this being built up from the earlier like edges and like really basic things. These textures then get built up into patterns. Like here, this seems like a packet. This seems like some kind of like fuzzy fur, or like flowers or something like that. You then get like components of an object. Like this seems like some cloth-like thing, flowers. This seems like a kind of, I don't know, some kind of user interface, a bunch of buttons. And then in the really late layers, you now seem to have these like meaningful objects, like buildings, people, eyes. And at the moment, we're just visualizing neurons in isolation. But it seems pretty plausible to me looking at this, that these later things are like built up out of simpler things. Like that the network is trying to figure out how to understand images, and it's realized that images are made up out of simpler building blocks that it can combine together. Yeah, the other fascinating thing is that we trained this to classify images. Yet, by looking at just the parameters of the network, you have enough information to reconstruct an image. And the key lesson here is that if you want to solve a difficult task, often the most efficient solution is to be general. And this is one of the like most fascinating and surprising things about machine learning, in my eyes. Things just get more and more general over time. Yeah, and the second lesson is that abstraction seems to be a really powerful technique. And as a mathematician, I find it incredibly satisfying that a powerful thing that I just told to figure out how to recognize images decided to break them down into simple bits, build the simple bits up into more complex bits, and build those up into even more complex bits to get to a final answer. Like, this is exactly how I think. And it's really satisfying to me that this just seems to be a fundamental truth of how to solve problems like this. A few interesting things you get out of this. So we pick the same neuron, and we look at what makes it really positive and what makes it really negative. And these are completely unrelated things. This is a bunch of like corkscrew style stuff that seems to be detecting like snakes and swans' necks. This is a bunch of like balloon style stuff. And this is weird. So it turns out that this seems to be a property that emerges from the fact that we use a ReLU activation function. So if you recall, networks are a composition of apply simple linear maps or image kernels, and then apply a nonlinear thing to them. And the nonlinear thing is often this like max of 0 and the activation. And this means that you can just have the same neuron and have like a coefficient of +2 to one thing and a coefficient of -2 to another thing. And these are just going to be, this is never going to be activated at the same time. Because if it's positive, this is activated, this is 0 and ignored, otherwise it's the reverse. So each neuron can actually do double duty, which I think is kind of cool. Another really awesome thing. So what happens when you so a neuron is just like a coordinate. And it's kind of weird that when you visualize a particular coordinate of a vector, you get something so meaningful. Because you could visualize any direction. So a natural question to ask is, what happens when you visualize like the sum of two neurons? And it turns out that the thing you get is like a combination of the meaning of the two neurons. So like, this is a black and white neuron. And when I combine it with this, I get a black and white thing. When I combine it with this, I get a more black and white thing. When I combine it with this, I get a more black and white thing. When I combine these, I get like, from these curved things, I get more square and angular things. And it just seems incredibly cool to me that there is like this linearity of meaning. Also, just a note, this thing that I'm on with cool graphics is a thing made by the authors. It is like the academic paper that the team put up. This isn't like an accompanying blog post or anything, because this journal, distill.pub, decided that archive PDFs are a terrible way of conveying meaning because you can't have things like this, and so decided to just make a website where you can actually have interactive graphics and link to your code. And it makes me incredibly happy that interpretability researchers have made some of the best written, most understandable and interactive papers I've ever seen, or most interpretable papers I've ever seen. And I'll link to all of the stuff at the end to play around with yourself. Final interesting thing is there's this notion of high-low frequency detectors. So these are neurons where half of the thing they're detecting is like high frequency, like this kind of blurry thing, and the other half is smooth, low frequency. These seem to be really useful. They're pretty simple, and we don't really expect them to be there. And there are currently some neuroscientists seeing if this is a thing in human vision, because if computers have found this useful to understand the world, maybe our eyes did too, we just haven't noticed it yet. No idea if this is true, but it would be incredibly awesome if it was. End subchapter 1. So, the next natural question is, can you use this understanding of what's actually going on to help humans understand the network? And turns out the answer is yes. So, yeah, and it's like a challenge to make a good user interface, because you have this really complex high-dimensional thing, and you need to make it human comprehensible. And so one tool they've created that I think is really cool is what they call a semantic dictionary. So the idea is you can hover over like an area of the image, and that pixel has like a vector attached to it. This like A44 thing, and that's just like a collection of numbers. But this is not human meaningful to humans. But the biggest numbers in that are like the most important neurons. And if neurons correspond to concepts, then this should be meaningful. And so what they do is they take the biggest numbers, the neurons they correspond to, and they visualize those neurons. And this is a way to understand what it's looking at. So like, if I look at the nose, then there's this thing that looks like a dog, like a fox, or like an animal face. I'm not really sure exactly what these are, but when I look at them, I have a much more visceral sense of what the network is actually doing. When I look at this eye, it's clearly looking at like eyes and animal faces and like the area around the face. When I go over here, it's clearly looking at ears, and different kinds of ear detectors are going off. When I go over here, it's looking at like a cat's face and fur and like the structure of a cat's body. And this is like a thing that I could use to look at what the network is doing and actually get some insight into what's going on and what's important. So, general point here, generally for any point in space, there are a few neurons that really matter. And by visualizing them, you can like use human visual understanding to get a feel for what's actually going on. A tweak you can make to this is rather than just visualizing the individual neurons, you can say, each point in space has a vector of activations attached to it. This is saying, this neuron's really important. This neuron's kind of important. This neuron's kind of important. Most of them aren't that important. Can I make a super stimulus that gets me this ratio of neurons as like strong as I can? And you can use our same feature visualization techniques for that, because this is just a vector. This is just like a linear combination of neurons. And when you visualize that, you get things like this, like really focused on a dog's nose thing. When you go over here, you get something that's really focused on ears. When you go over here, like eyes and noses are dominant. So it's kind of like a cow, and that's kind of weird. When you go over here, it's really about legs and fur. So from a certain point of view, this is what the network is seeing at that point in space. It's filtered out all the things that don't matter, and it's focused on like the most meaningful features. And because this network is trained to be good at recognizing dog breeds, it's really focused on things like eyes, nose, ears, fur, because these are predictive. Skip that part. Another thing you can do with this is making it human comprehensible. So if we look at the final output, this is I think it's a Labrador Retriever, or possibly a Beagle, and we look at a particular layer, then there are a few neurons in that are really important for the final answer. You have neurons that detect, say, like fire hoses, that are just not triggering, not relevant, but you have a few that really matter. And what you can do is you can say, which neurons activate the most? Okay, an ear neuron activates the most. Which bits of the image activate that ear neuron the most? Which bits of the image have the highest gradient? And which bits is it most looking at? These are all things you can figure out by just say tweaking the pixels of the input and seeing what changes the ear thing the most. And you can see the ear thing is looking at the ear. This thing that looks like it's looking at the head and eyes is looking at the head and eyes. Like, this overlay is showing us what the network is looking at. And you can tell that like most of these things just don't really matter. It kind of looks at this cat, but then decides the dog is more important and focuses on the dog more. And I just find it incredible that you can have a user interface like this that is so helpful and meaningful. And there's also a bunch of like underlying maths that I haven't quite got my head around how they're doing this, because they need to figure out how to represent this big tensor of activations. And they're using some techniques of matrix factorization to do this. And if this interests you, I highly recommend reading the paper for the details. The final thing you can get that's interesting is, so I've talked a lot about how these features seem meaningful, but And they seem like they're built up out of smaller things. But how do we know this? So this bit is visualizing, okay, so how are these neurons feeding in to this later thing that I care about? Like this label, how are the earlier neurons feeding into the intermediate neurons? And we're visualizing this with like thick lines between them. If there's a big relationship, thin lines if there isn't. And from this we can see that, oh wow, the ear thing is being built out of like other things that seem meaningful. This seems to be recognizing dog's faces, and it's actually being used. And this is a thing that extends pretty well. You can even use this to debug networks. This network on this image thought there was a bit that looks a bit like a tennis ball, and digging in with these tools, the researchers found that it was actually looking at this bit of grass under the dog's mouth, and because it was green and curved, it triggered a tennis ball neuron. And by digging in with these tools, they were able to find it. In the interests of time, I'm going to skim through this chapter. The important point of this chapter is that, well, the coolest thing of this chapter is our goal is now to look at the dataset and to understand how the neuron sees the dataset and what it learns from that. And one cool thing that they discovered when they were looking at these two different classes, grey whale and great white shark, and seeing which neurons were most discriminatory, or which bits of images were most discriminatory, they found that the things they were looking at, which detected the teeth of the great white shark, were kind of the same, similar to the things that were detecting baseballs, and like the stitching along baseballs. And they were able to test this belief by creating this picture. They took a whale and they just stuck a baseball on there, and it now really looks like a great white shark. And this is obviously cherry-picked, but I just find this fascinating because this is a perfectly human, understandable adversarial attack on a network. We can make a thing that looks obviously dumb, but by understanding the internals of how the network is classifying things, you can get something meaningful out of this. And they just took all of the pictures of grey whales and just shoved a baseball in the corner, and that messed up about 20% of it. Okay, and the stuff on user interfaces. So I now want to talk about an idea called circuits. So here I'm going to be trying to dig in a lot more detail into how is the network calculating things? What is actually going on inside it when it's processing and thinking? And the first interesting thing to note is that the ReLU activation function we have allows us to do basic logical operations. Because it's this like max 0z, if you add together two activations post ReLU, if either one is active, the final thing you get is going to be positive, because the inactive one's just going to be 0. If you negate a neuron, then it becomes, it's like a not operation. If it was going to be big, it's now 0. If it was going to be 0, it's now big. This is important because these basic operations of OR and NOT are really human understandable. And it turns out these are things the network actually uses. So, for example, this is a black and white neuron that seems to detect black and white. And when you dig into the things feeding into it, it's a bunch of, it's like the combination of a bunch of color detectors, all with negative coefficients. They're basically saying, or this type of color, or this type of color, or all of them together, and then saying not to all of that. And that's how it creates a black and white detector. Another interesting example, here's a weird neuron. We try to visualize this weird neuron, and we get like 2 dogs with a nose in the middle, and like what? And when you look at the dataset, you just got a bunch of dogs facing different directions, And so it turns out that this neuron is a pose invariant dog detector. And the way it's built is there are some neurons that detect right-facing dogs, some neurons that detect left-facing dogs. It combines these together into right and left-facing dog neurons, and then takes the OR of both of them to get a pose invariant detector. And that's why you get this like weird effect where there's two dogs, because you've just unioned them into one meaningful feature. Because it doesn't matter if the dog's facing right or left for whether it's meaningful in the image. Also, apparently, it's squirrels, because squirrels and dogs clearly look the same. So, bringing this together, this is an idea that the researchers call circuits. So, the idea of a circuit is taking, if features are, if neurons are like human comprehensible meaningful features, then the next guess is that the network might connect up small amounts of these features in specific ways to create larger features in a way that's human comprehensible, like this. And they make three bold speculative claims that neurons are actually features with meaning we can understand, that these features do get connected up in human understandable ways, and that these ways appear across different models and different tasks. And this is a very, very speculative claim, but I'm going to dig into a particular example of the circuit that I find pretty compelling evidence of this. This talk is probably going to overrun by about 10 minutes. My apologies. So, the idea is what are called curve detectors. So, it turns out that in this network we're studying, there are these 9, or actually 10, I had to cut off one to fit, neurons that seem to be detecting curves in different orientations. And they dug really deeply into these, and the team seems to have found a lot of interesting results about how these are meaningful. And I'm going to try to give the evidence from their paper that I found most compelling, that this really is a circuit. And this really is like a human comprehensible, meaningful motif that comes up again and again. They focused on one particular neuron, this orientation of curve. There seem to be neurons in all kinds of different orientations. The similar results, I think, held for the other ones. So the first thing you should always look at is which dataset examples trigger this. These seem like upward-facing curves, or downward-facing curves. The second thing you can try is the trick we did earlier with looking at the image and taking a neuron and seeing which bit of the image activated that. You look at the gradient of the neuron with respect to each pixel in the input, and you see which lights it up the most. And it seems like the things that light it up a lot are the ones over here, which are downwards-facing curves. And things that light it up the least are these upwards-facing curves, these opposite orientation things. You can even just give it hand-drawn curves, which it turns out are like super stimulating. It lights up at 25 standard deviations when you give it a curve like this. These 10 curve detectors seem to cover basically all of the angles if you feed in this like rotation of curves into all of them. This is just saying, given an orientation of curve, how much does it trigger each of these detectors? I'm not super sure what's happening here and here. And these seem to be used later on for meaningful features. For example, this is built out of a simpler previous curve in like a really comprehensible way. It's just like adding together a bunch of copies of a smaller curve, basically just like a tangent curve. And it's saying, you probably have a big curve if locally it looks like a bunch of small curves stuck together, approximately. It also gets used in things like spirals, circles, eye detectors. See the paper for details on those. And they have some unpublished research yet to be published research, where they claim to have just directly coded an algorithm like this to make a good curve detector. And this seems to come up in a lot of different models. It seems like this isn't just a quirk of the particular thing they studied. It seems like the ability to understand curves in like somewhat different ways seems to come up across lots of different models trained on ImageNet, and even one model that's trained on like a different image database. One fun fact about these is when you compare them to how a human labeled an image for how curvy it is, it did pretty well, to the point of being literally superhuman, because some of the ones it misclassified were actually curves, just subtle curves the researcher missed. So it literally beat a human at detecting curves. And yeah, you can do cool things with this. Like here they took an X-ray and where they wanted to highlight these edges, like the interesting features. And here is like a kind of really basic standard edge detector you might use. Nowhere near state of the art, but just like a basic thing to give you an idea of this is a hard problem. And here's what happens when they just told the network, detect curves and light them up. And like they didn't train it at all to be able to do this. This is just a property of a thing trying really hard to learn how to recognize images. You can also get interesting object detection results out of this, where they trained it to optimize these curves to like maximally activate the neurons. And cool. So what are some practical implications of all this? So I'm going to dig into some yet to be published research a friend of mine's been doing with applying these techniques to reinforcement learning. Just to give you an idea, all of the last chapter of research about circuits came out earlier this year. Like this is a really contemporary area of research. And so he was studying a reinforcement learning agent that was trained to play this like Mario style game. And he found that he could look through the eyes of this network and see, oh, it finds coins interesting, and it finds enemies interesting, and it's highlighting those in different ways. And this time it wasn't quite neurons, they had to take linear combinations of neurons, but there were some techniques they could use that worked. And they were able to extract this and overlay it over the picture. And this is interesting because it just helps you understand what's going on. You can diagnose mistakes, where say a mistake's part of the wall for a coin to look yellow and roundish, and you can tell because it lights that up. But the really fascinating thing is you could directly edit the network to change how it acts. So here's a level where it just goes normally, it just figures out how to get to the coin, and now we delete the neuron that's able to track buzzsaws. And it goes from being able to play perfectly to being able to play perfectly, except it can't notice buzzsaws. When we delete the neuron that detects enemy going left, it can play perfectly, but it can't detect the enemy. And these aren't cherry-picked examples. They gave them like 10,000 runs, and in 12% of them, it dies in the buzzsaw when you delete the buzzsaw, compared to like a fraction of a percent in the original model. And I think that there's a lot of really interesting implications if this work goes somewhere and can be generalized. Like the ability to find a way the network is doing something wrong or doing something badly and directly editing it seems incredibly powerful. And if you can have transparency tools look into a network and see what it's doing, then you can debug it. Then you can see if it's mislearned the thing you told it to do. One example, which I'd be pretty excited to apply this to, though very far in the future, is this idea of algorithmic bias. When you train a network to, say, figure out who to arrest for crimes, there's a lot of data of black people being arrested for crimes because the police are racist. So the data is racist. So the network learns this as a predictor. And this is a clear bias, which is really hard to get rid of. So if we could get to the point where we could identify the bit of the network that's tracking race and delete that, that sounds incredibly exciting. Obviously, this is like very far from that point, but I'm really excited about this research direction. And I also just find it really fascinating that we train something to be really good at solving a specific task, and it derived this general idea of looking at small, simple concepts, building them up to bigger concepts, building up to more and more abstract things to answer the original question. Again, to solve a hard task, it seems to be a fact of the universe that an efficient solution is to be general and be abstract. And in some sense, this is probably why humans can think in the first place. The task of reproducing and surviving in the ancestral environment selected for good general purpose thinkers. We can solve arbitrary new problems when they're given to us. One really interesting direction this research could go is an idea called microscoped AI, where we use AI as a tool for understanding the world better by just training a network to understand some complex data really well, like say data from a particle accelerator, and then see if we can extract out concepts from this, and see how the network is putting things together, and see whether there are any human understandable concepts we could learn from that. And this is very far from that point, but that seems like a possible place they could go. And so, in conclusion for that chapter, I'm really, really impressed by these results, as you could probably tell by how excited I am. And this is just one team that's got into this area over the last few years and is doing a lot of really good work. Not quite one team, there are other people working in this field, but it's a very, very small field. And this is really these are really limited results. It's pretty easy to fall prey to cherry picking, though this team's been very good about accounting for that, running falsifiable experiments, giving a lot of examples and data for you to go through yourself. At the end, I'll link to a visualization of every single neuron in the network and giving you their code to run your own experiments. And this is all pretty limited to vision, where because of how convolutional networks work, it's unusually easy to get these abstract concepts. And it isn't obvious that it's going to transfer, but it seems like if it could, that would be an incredibly important thing to research and learn about. And finally, it wouldn't really surprise me if there is a lot of low-hanging fruit here, because most academics studying machine learning are really focused on performance. There are these datasets like ImageNet, and it's a big deal if you can get better performance on a big dataset than somebody else has before you. These are called benchmarks. And so a lot of the academic incentives are focused on performance. And as a mathematician, this deeply, deeply offends me. The interesting part is the concepts and the understanding. And there is a clear systematic bias in ML academia away from trying to understand things deeply. And this means that it wouldn't be that surprising if there are a lot of things to understand that we haven't got to yet. And so I think this is a really exciting area of active research. I'm going to skip through chapter 3 because, God, I run over. So, in conclusion, I think that machine learning is a really interesting field. And one of the really weird things about it is it's only about 8 years old. It doesn't have these deep ideas and maths built up behind it. It's all about applying simple ideas and concepts in really clever and creative ways and fiddling with it to make it work. And I think that there's a lot of interesting problems. Hopefully my display of things I find most fascinating has convinced you somewhat of that. And these are really important problems because this seems like a really big part of how society, this is going to shape a lot of how society works over the coming years. And I think there's a lot of fascinating questions that aren't being answered, in part because people who are working on this don't focus on the understanding and the concepts behind them. So there's a lot of unanswered questions. And if this kind of things excite you, I think this is a really good area to try to become an academic in. There's a lot of interesting research questions, there's a lot of funding for it, and the stuff you do really matters. So if the stuff I talked about in this have resonated with you, here are some of the resources I'd most recommend for learning more about this yourself, because it just doesn't take that much time to kind of get up to speed with the very basics in ML. There's a course I'd very highly recommend called the Fast.ai course, and You can read these beautiful interpretability papers I've been quoting at distill.pub and find all the graphics and code. Ignore this point because that's about chapter 3, which was cut due to time constraints. And yeah, that is my talk. I think ML is an incredibly exciting area. I think that as mathematicians, this is an area which isn't that hard to enter if you want to. And I think this is important and fascinating. So if any of you are interested, I hope this has been a good starting point. Does anyone have any questions?
I'll start off with a really vague one. So you're talking about how these neural networks think kind of similar to the way humans do, right? So for example, this use of abstraction to solve problems and this kind of thing. How much do you think of this is really inherent to the way thinking works? And how much of this comes just from the fact that humans made the network, humans designed how the layers work, which layers there are, and it just this very high level structure is there in the way the network is built already?
That's a good question. I have no idea. I like to think that there is something deep going on here, but I'm also biased because I'm a mathematician and I like things to be conceptually pretty and human understandable. I mostly phrase this as, I think this is an area I'd really like to see a lot more research on it, because we just don't know at the moment. It wouldn't surprise. So I guess we have one data point of a general intelligence, humans, that evolved. And we think in these beautiful, pretty concepts. And this seems like pretty compelling evidence to me that there's something inherently special about thinking in concepts. But also, n=1 is not a good sample size, so we really don't know. Sorry. By the way, I've just I've just sent some stuff into the chat. I have a feedback form, and I'd be super curious to hear people's thoughts on this talk, both so I know what went well and for ways that future talks can be better. So I'd really appreciate you fill that out. And I've made a page on my website, which is a ton of references, resources, links to all the graphics, links to further reading, and links to ways to get into machine learning if you found these ideas exciting. And these are both in the chat. And I'll also post them on the Facebook event. We have a question from Shavindra. Are there efforts to relate concepts in neuroscience and improving efficiency of neural networks? So this is a question I'm pretty confused about. So everything I'm about to say is pretty much contentless and meaningless. But yes, there are efforts. No, this isn't necessarily going to work. And no, this isn't the only way people do things. In general, the way networks work was pretty inspired by neuroscience and biology. The way convolutional networks work is actually pretty similar-ish to how vision works, but there's also a lot of important differences. And this means that ideas from neuroscience are kind of interesting and a good starting point. And again, we have one data point of a general intelligence. Learning from this seems pretty sensible, if we can infer as much as we can. But there's no guarantee that this is going to work. So again, it's an empirical field. You try things, you hope they work, you tweak them and work at them, but you also learn how to give up if your things don't seem to be working. Anyone have any other questions?
Right. Okay. If there aren't any other questions, let's thank Neel. There's a lot of really cool stuff in this talk. So yeah, thank you.
Thank you very much all for coming.